Hello, everyone. I okay. Let's consider so the other day we considered example 18 where the W space is defined, right, with these five entries in R5 or C5 space where two conditions are given, A1 plus A3 plus A5 is 0 and A2 and A4 are equal. Then, as I showed the other day, I could express A1 and A2 in terms of the others. So the idea was to describe A1 and A2 with respect to the other three entries. Then, given this solution, given this vector, I replaced A1 and A2 with these newly obtained expressions. And then I split the vector as the sum of three vectors, one having only a3, and the second one has only a4, and the third one has only a5. Then I could rewrite each vector as a certain number multiple of three vectors, and you can easily check that these three vectors are linearly independent. And when I say they are linearly independent, as I mark it there, you can just look at the locations of A3, oops, and when I look at the third entries 1 0 0, then that means when I look at this 1 0 0, that means the this vector, the first one, cannot be written as a linear combination of three vectors, right? So my point is negative 1 0 1 0 0 cannot be written as, say, A times 0 1 0 1 0 plus B times negative 1 0 0 0 1. You cannot write down the first vector as a sum of the other two. And I could just notice this fact by just looking at the third entry, because the vector on the left has the value 1 in the third place, while the other two have just zeros. So regardless of the values of A and B, right, the third entry in the vector on the right will be always 0. You cannot make 1, right? In a similar way, when I look at the fourth entries, the second vector 0 1 0 1 0 cannot be written as a linear combination of the first vector and the third one, because because the fourth entry on the left is 1, while the other two have 0 in the fourth place. So the second vector cannot be written as a linear combination of the other two. And when I look at the fifth entry, only the third vector has the value 1, while the other two have the value zeros in the fifth place. So that means the third vector cannot be written as a linear combination of first two vectors, right? So please remember that if given these three vectors, so we have one fact that given V1 up to Vn, the set is linearly dependent. That was equivalent to saying that some vector can be written as a linear combination of the others, right? In this example, we have three vectors. V1, V2, V3 are considered. And which I just showed that V1 cannot be written as a linear combination of V2 and V3, and V2 cannot be written as a linear combination of V1 and V3, and V3 cannot be written as a linear combination of V1 and V2. Okay, so that means no vector can be written as a linear combination of the others. That means these three vectors are linearly. So because of this, these three vectors are linearly independent. Okay, so let me go back. So that's what I showed. So let me go back to the example. So in this example, W is a certain subspace generated by these three vectors, because when I choose any arbitrary vector from W space, that vector is a linear combination of these three vectors, and these three vectors are linearly independent. So these three vectors will form a basis. So the dimension of W that counts the number of vectors in a basis, it will be 3. Of course, note that this is not the only basis. You have infinitely many different possible bases. Okay? But this is just one example. In example 19, so suppose that we consider a large vector space M sub n by n. So that is the space of the collection of all the n by m matrices. Now, previously we considered the certain basis of that space, right? So we considered the set of e to the ij, and so which is, so e to the ij has just so it is an n by m matrix. It has the value 1 in the ith row, jth column, but all the other entries are zeros, right? So this is e to the ij was one basis for this m sub n by n space. So what was the dimension of this m sub n by n? The dimension of m sub n by n will be 1/2 times n plus 1. Okay. So that was the dimension of the space. Now, in this example, we want to consider its subspace W, which is defined by the set of diagonal n by m matrix. What is a diagonal matrix? A diagonal matrix is a matrix whose non-diagonal entries are zeros. Okay, so so if I consider this, so the first matrix has 1 in the first diagonal entry. E to the 2 is the matrix having 1 in the second row, second column. And e to the 3 will have the matrix having 1 in the third row, third column, and so on. So this set will form a basis, meaning W is, so that means if I call this guy by S, then span of S is definitely W. You can show that. And S is independent. So this S is a basis. So dimension of W will be N. Another example. Uh, okay, we want to consider the same space, M sub n by n matrix. And in this case, in this example, we want to consider some subspace W, which is defined by the set of symmetric n by m matrices. What is a symmetric matrix? Symmetric means the matrix and its transpose are the same. Then, okay, before we consider this, let us consider some simple situation. How about W of M sub 2 by 2 case with real scalar field? Then, so if I consider, say, 1003 is one example of in that matrix, or identity matrix is also included in that space, or even zero matrix is included. As I said, the symmetric, okay, so these are all examples of the symmetric matrix. Now, then for this W of M sub 2 by 2 space, how about e to the 1 1, e to the 1, e to the 2 2, or okay? So and there are many others. Symmetric means, so we have 1 3 3 0 and 2 1 1 5. They are all symmetric matrices, of course. Now, if I consider e to the 1 1, e to the 1 2, e to the 2 1, e to the 2 2. In other words, e to the 1 1 is 1 0 0 0 matrix, and e to the 1 2 is 0 1 0 0, and e to the 2 1 is a matrix with 0 0 2 1, and e to the 2 2 will be 0 0 0 1. And if I consider this set of four matrices, then, as I said, this is not a basis of W because because some matrices in the given set, like 0 1 0 0 or 0 0 0 1, are not symmetric. They are not symmetric, meaning those vectors, okay, those two matrices are not in W space. So you cannot consider so you cannot consider that choice of matrices. Instead, we can consider the following matrices: A to the ij, where A to the ij is the n by m matrix having 1 in the ith row and jth column, ith row, jth column, and one more one in the jth row and ith column. So for example, in this 2 by 2 case, A11 is a matrix of 1 0 0 0, and A12 will be 0 1 1 0. A22 will be 0 0 0 1. Something like this. So we want to consider a to the ij, okay, where I goes from 1 to n and j is greater than or equal to I. So that means we want to consider a sub 1 2, but even though by definition a sub a to the 2 1 will generate the same matrix, but we do not want to consider this because in that case a to the 1 2 and a to the 2 1 will be the identical. So we do not want to consider a to the 2 1. We want to consider only a to the 1 2. So when n is 2, we have only those three matrices. So for and you can show that any any vector in W or any matrix in W, symmetric matrix, can be written as a linear combination of these three matrices, and you can easily check that they are linearly independent. So dimension of W, when I consider m sub 2 by 2, that will be 3. And in general, as in example 20, if you consider all the matrices where I goes from 1 to n and j goes from just I to the n, then if you add them, the dimension will be this. So that is the dimension of W in general. Now, corollary is this. If W is a subspace of finite dimensional vector space, then any basis for W can be extended to a basis for V. Okay? That is trivial. And example 21, but let us check some example. So the set of all polynomials of this form. So as you can see, I'm just considering only even powers of x. A naught, meaning a naught is the constant term which is the coefficient of x to x naught. And then we have x squared, x to the fourth, and then up to x to the 16th and 18th. And then we have some coefficients. Now you can show that. Please check that this is, you need to make sure that this collection, this set of polynomials of such form will be a subspace. And you can easily check that the set of these even powers of x will form a basis for W. Okay. And I can extend this set to form a basis for the original vector space. So three things are mentioned. First of all, this set will be definitely a subspace of P sub 18. Second, this will be one basis for W space. Thirdly, I can extend this basis of W to form a basis for the original space, P sub 18. Of course, you can just combine x cubed up to x to the 17th, then this union will form a basis for P sub 18, right? So it is trivial, but yeah, we have this. Now, this example is a well, many applied mathematician or people in, yeah, some application or engineering people like this Lagrange polynomials. So what is this? So suppose that I have n plus 1 numbers from C naught, C1 up to Cn. And I want to define f sub ix by this expression. So here in the numerator, I have x minus c naught, x minus c1 up to x minus ci minus 1. And then in case of this f sub I function, I skip x minus c sub I. So from x minus c sub I minus 1, I jump to x minus c sub I plus 1 up to x minus cn. And in the denominator, x is replaced by ci. And since, okay, here I'm assuming that this c naught up to cn are all distinct numbers, the denominator is not zero. So let me give some example. Okay, that might be easier. So for example, um, let me consider three situations. So C naught is 1, C1 is 2, and C2 is say 4. Something like this. So I have three numbers. Then F naught is defined by x minus C naught is skipped, so x minus 2 times x minus 4 divided by 1 minus 2, 1 minus 4. And f1 is defined by x minus c naught, which is 1, and x minus, I skip x minus 2, and then you go to x minus 4. And then each x in the numerator is replaced by c1. So 2 minus 1 times 2 minus 4. And f2 is defined in a similar way. X minus 1 times x minus 2 over 4 minus 1 times 4 minus 2. So I can define these three functions. They are all second order polynomials. So when I consider three three values, C naught, C1, C2, I'm introducing three second order polynomials. And what is the property of F naught? When I evaluate F naught at C naught, which is the value 1, if I plug in 1, what do I have? You have 1 minus 2 times 1 minus 4 divided by 1 minus 2 times 1 minus 4. So the numerator and denominator are identical. So the value will be 1. If I plug in C1, what do I have? What is the C1? C1 is 2. When I plug in C1, what will be the value of x minus 2? It will be 0. So f naught of C1 will be 0. And what if I plug in C2? 4. Then x minus 4 will become 0. So this term will be 0 as well. In case of f1, when I plug in C1, that means I'm plugging in the value 2. Then we have 2 minus 1 times 2 minus 4 divided by 2 minus 1 times 2 minus 4, which is 1. And then if I plug in C naught due to x minus 1, this f2 of C naught will be 0. If I plug in C2, due to this x minus 4, the term will be 0. And in a similar way, f2 of C2 will be 1, while f2 of C naught or f2 of C1 is 0. They are all zeros, right? So I define three polynomials, f naught, f1, f2, and they have this property. In short, given f sub I, when I plug in C sub j, if I and j are the same, the value is 1. If I and j are different, the value is 0, right? And what is the degree of the polynomial? They are all nth order polynomials. If I have three numbers, you get second order polynomials, right? So if I have n plus 1 points, then, and if these numbers are all distinct, then you get, okay, this is a degree polynomial of degree n, and this polynomial has a very special property that when you plug in C sub j, the value of the function as C sub j will be either 0 or 1. If I and j are different, the value of the function at C sub j will be 0. If I and j are equal, the value is 1. So such polynomials will be called Legendre polynomials. I'm sorry, Lagrange polynomials. Okay, so they are called Lagrange polynomial. So it is a polynomial. Suppose that their linear combination is 0. Okay, for some numbers. So suppose that this linear combination of these functions is 0. Then, given this zero function, so this is a zero function. So that means when I evaluate that function at any point, even C sub j, the value of the function at C sub j will be 0. Now, let us look at this expression. This is the sum of certain values. So I can rewrite this as, okay, so, okay, for this one, so when I look at this fi of C sub j, this value will be either 0 or 1, right? This value is either 0 or 1. When is it 0? If I and j are different, the value is 0. If I and j are the same, the value is 1. So when I goes from 0 to n, okay, at some point, this I will be the same as j, right? So when I equals j, so when I equals j, f, when I and j are the same, fi of C sub j will be the value 1, and at that point, the coefficient is a sub j, right? If I and j are different, the f sub I as c sub j, so here fi c sub j will be 1 if I is the same as j, but fi c sub j will be 0 if I and j are different. So if I consider this in this summation, this value will be either 1 or 0, and only one coefficient will survive when I and j are the same. Otherwise, all terms will be disappeared. So, so the expression on the left will be the same as a sub j, and that a sub j must be 0. So we have this. A sub j will be 0 for all j value. Then what does that mean? When I consider this linear combination of these functions, and if I assume that this linear combination is a 0 vector, then I could derive this result. Each coefficient must be 0. That means this f1, f1, f naught up to fn, these functions will be all linearly independent. Okay? Okay. Now, we know that this P sub n space has the dimension of n plus 1. So I know that this space has dimension n plus 1, and I found n plus 1 linearly independent polynomials in that space. So I found a basis. This beta will be a basis. Please remember that if I know the dimension, if the dimension is n plus 1, then, and if I have a set of, if I have a generating set with n plus 1 vectors, it will be a basis. If I have a linearly independent vectors, I mean n plus 1 linearly independent vectors, that will be a basis, right? So this set beta is a basis. Then, okay, so it is a basis. So that means it will be, this beta will be a generating set, right? It is a basis, so that means beta spans this space, meaning that each vector in that space can be written as a linear combination of the vectors in a of this basis. So if I choose any polynomial in that space, that polynomial can be written as a linear combination of these basis vectors. Okay, that was simple, but we can go one step further. Okay, then what is this BI? How can I find this BI? Okay, given this equality, if I plug in C sub j to this expression, on the left we have G at C sub j. On the right, I need to evaluate this function, this polynomial as C sub j. And please remember that f sub I as C sub j will be 1 or 0. If I and j are the same, the value is 1. When I and j are different, each fi will be 0. So this is the summation of n plus 1 values, right? And when I and j are equal, that fi of c sub j will be 1, and at that point, the coefficient will be b sub j. All the other terms will be 0. So we get this equality. So that means b sub j, the coefficient of this linear combination, will be the value of this polynomial g at c sub j. So if you plug in c sub j to the polynomial, then I can find this expression. Do you understand what I'm saying? So any polynomial can be written as a linear combination of these basis functions, which are Lagrange polynomial. So let me go back to the previous example. So if I consider this, and if I consider any polynomial, say g of x defined by say 1 plus x plus 2x squared, if I have something like this, then what is the g1? That is 1 plus 1 plus 2, which is 4. G of 2 will be 1 plus 2 plus 4 times 2 is 8, so 11. G of 4 will be 1 plus 4 plus 16 times 2 is 32, so 36 is 37. So this gx, this gx, 1 plus x plus 2x squared, can be written as 4 times f naught plus 11 times f1 plus 37 times f2. Okay, so that's the result of that example. So any polynomial in the space can be written as a linear combination of those three polynomials, and those three coefficients used in this expression can be easily found. We can just evaluate the polynomial at the given C0, C1 or C2. So anyway, uh, we will use this result just to once later. Okay, so I wanted to skip this example, but anyway, since I need to use this result at some point in the future, I'm just introducing this example. But anyway, this is an interesting example, and you can check, you can read this in more detail yourself. And if you have any questions, let me know. Anyway, so that was the end of chapter 1. So in chapter 1, we considered some definition of a vector space, subspace, basis, and we consider some special cases where the vector space is Rn or Fn space, and in that case, we could consider certain matrices and so on, right? So that was, yes, the end of chapter 1, and then let's go to the next one. Okay, so in chapter 2, we will consider transformations. So, so transformation is just a mapping. It is a function. It is a map. What is a function? What is a map? You are given two sets, and you assign certain element in one set to another, to a set, to an element in another, to the other set, and we have certain rules, right? So I guess you know what a function is. So this transformation is equivalent to a function in our class. Now the point is we want to consider something called a linear transformation, a linear function, linear mapping. Okay? Then in chapter 2, okay, so given some linear mapping, whatever it is, okay, I will define that in a moment. So we will consider a linear transformation, and then somehow we want to express that linear transformation with respect to a matrix. The Y matrix, because it is very easy to manipulate. Okay. So that's what we are going to do in chapter 2. Okay, so in section 1, let us define the linear transformation and null space and the range. So suppose that we have two vector spaces V and W, and suppose that they have the same scalar field F. So meaning they both the spaces are defined over, say, the real numbers or the complex numbers. Okay, so V and W have the same scalar field. Now, when I use this notation and if I call this, okay, then we that is representing a function, a mapping from V to W. So when I say a function, that means when I say a function from V to W, as you know, for each element in V, we assign some element in W, right? So that we can define some connection between these two. Now, we say this function is linear. This is important. We say the function mapping is linear if it satisfies these two properties. So for any vectors x and y in V, t of x plus y will be the same as t of x plus t of y. And when I consider scalar multiple c times x, and then it's t of c of x, c times x will be the same as c times t of x. Now, in this definition, this plus sign is the addition of vectors within V space. The plus sign on the right is the addition in W space. So the requirement A says you can perform the addition in the domain, and then you can consider the mapping T, or you can consider the images of x and y, and then you can consider their summation in the codomain. In either way, that you must have the same result. In part B, Cx, this C is multiplied in the domain. This C on the right is multiplied in the codomain. So, statement A says you can add. So I have V space and W space, and I have x and y, and x plus y will be some vector in V space because we are considering a vector space. And W, so x will be mapped to t of x, y will be mapped to t of y, and x plus y will be mapped to t of x plus y. Statement A says, okay, you can map x and y separately, and then if you add t of x and t of y, you get t of x plus y. Okay, so when you add, you get t of x plus y. Or you can add x and y in the domain to get x plus y in V space, and then you can find the image. Or you can multiply c to x in the domain, and then you can consider its image. Or you can consider t of x, and then you can multiply c to get t of cx. So if your function satisfies this property, then that mapping will be called a linear transformation, linear mapping, or simply linear. Well, if t is a linear, then t of 0 will be always 0, right? Because there are several ways to prove that t of 0 plus 0 must be t of 0 plus t of 0, and that is t of 0. So from this equation, if you subtract t of 0 from this equation, then On the left, we get 0 vector. On the right, we have t of 0. So they must be the same. So that means the origin is not changed by the linear transformation. If t is linear, then then if t is linear, then when I consider t of cx plus y, that is the same as t of cx plus t of y, and c can be taken out of this. So if t is linear, we get this result, right? So this direction can be easily proved. I mean, then how about the other direction? So suppose that I have a function mapping t satisfying this. Then, first of all, when c is 1, you get the requirement a, right? Now when then you so in this case you get a. When y is 0, then since t of 0 is 0, when y is 0 vector, you get the axiom b, second requirement. So if the right hand side is satisfied, then that will satisfy two requirements for a linear combination, linear mapping. So your mapping will be linear. So instead of showing these two requirements, sometimes if you can show that your mapping satisfies this highlighted statement for any x and y pair or any scalar c, then your mapping will be linear. If t is linear, then we can easily derive this fact as well. And if t is linear, I can extend this statement to many vectors. So if I have, say, n vectors, then linear combination of those n vectors can be considered within the domain, and then you can consider its mapping. Or you can consider the images of those n vectors and consider the linear combination with the same weights. The result will be the same. If your t is linear, then this result is obtained. If this result is obtained for any n vectors and any coefficients, then your mapping will be definitely a linear mapping. Now, at this point, let me just clarify one thing. In calculus, in calculus, if I define f of x by x plus 1, the graph is a straight line. X, the slope of the line is 1, and this 1 represents the y-intercept, right? So that is the value of the function at 0. So for this function, f of 0 is not 0. As I said, in case of a linear function, the image of the mapping must be 0. There is no exception. That was the first condition here. That's the first result of a linear function. So if I have a linear function, the origin cannot be changed. The 0 vector will be always mapped to a 0 vector. Now, when I consider this function x plus 1, 0 in the x-axis is mapped to 1 on the y-axis. So this is not a linear transformation. This is not a linear mapping. Okay? So in calculus, some people call x plus y function as a linear function just because the exponent, the power of x is 1. But in our linear algebra class, it is not a linear transformation because the 0 is shifted. So please be careful. In example 1, so let me consider the following mapping. T from R2 to R2 space. This pair of A1 and A2 is mapped to 2A1 plus A2 and A1. Now, to show that this T is a linear mapping, let us consider an arbitrary real number C and two pairs x and y. So when I say two pairs in R2 space, then x has two coordinates, say b1 and b2, and y has d1 and d2 coordinate. Then cx plus y will define this pair so that its image is given by this. Now, if I consider this expression, c times tx, since the t of x is defined by this, c times t of x will give you, yes, this, oops. So that will be 2cb1 plus cb2 and cb1 vector plus 2d1 plus d2 and d1 vector. If you add these two vectors, then the first component is this and second component is this. Or if I rewrite this, you get this one, which is identical to the previously obtained result. So the mapping will be a linear mapping. Here is another example. Let us consider T sub theta, which is a mapping from R2 to R2. And T sub theta will map this pair. This pair, A1, A2, will define some point on this R2 or XY plane. The image is obtained by rotating this arrow the counterclockwise by degree theta. So this is the image of the previous A1, A2 point. Then this mapping will be a linear mapping. Okay, just a second. Yeah. Okay. And this will be a linear transformation. And we will call this guy by the rotation by degree theta. Okay. So given any point, A1 and A2, that red dot and blue dot is transformed to this red dot. Okay. Then how can I prove that this is a linear mapping, linear combination, it's a linear transformation? So I have, okay, so let me extend this. Let me draw the picture here and then, okay, so um, let us consider this right triangle. Okay, this is a small one with, so suppose that A1, A2, this blue dot has the angle alpha with the x-axis. So this angle is alpha. Then given this right triangle, the length of the arrow, so this length is by the Pythagorean theorem, the square root of a1 squared plus a2 squared. And when we consider the trigonometric functions, the ratio between hypotenuse and the base defined cosine, right? So so cosine alpha measures cosine alpha represents the ratio between the base, which is a sub 1 over the a1 squared plus a2 squared, and the ratio between the hypotenuse and the opposite defines the sine function. So sine alpha will be the ratio between a2 and a2 over the square root of a1 squared plus a2 squared. Okay, so if I use r to denote the length of this arrow, then a1 will be r cosine alpha and a2 will be r sine alpha, as I mentioned. Now, if I apply the same logic to the previous figure, when I consider the image, so the image vector t sub theta of a1 and a2, it will introduce the right triangle as well. And in that case, the angle between this arrow and the x-axis will be theta plus alpha. Since I just rotated the arrow, the length is still r. So the base, the x-coordinate of the image will be r times cosine theta plus alpha, and the y-coordinate, the length of the opposite, will be r times sine theta plus alpha. So, the image has x-coordinate of r cosine alpha plus theta and r times sine alpha plus theta, right? Now, if I expand cosine alpha plus theta, you get cosine alpha cosine theta minus sine alpha sine theta. That's what you learned in the trigonometry. And in case of sine alpha plus theta, when that is expanded, you get cosine alpha sine theta plus sine alpha cosine theta. And if I replace r cosine alpha with a1 and r sine alpha with a2, then that expression can be written by this. Okay. Now, if that's the case, okay, so here cosine theta, sine theta, they are just numbers. Please remember this. Okay, so even though this is a little bit complicated, so the t sub a1, a2 is written, say, some number, say a times a1 plus b times a2. And the second entry is c times a1 plus d times a2. So we have this. And then you can easily check that t sub theta a1 a2 plus t sub theta b1 b2 equals t sub theta a1 plus b1 and a2 plus b2 if your t sub theta is defined in this way. Also, t sub theta times c times a1 and c times a2 can be written as c times t sub theta of a1 and a2. So you can easily check this. Okay? So in that sense, this rotation is a linear mapping. Okay? So we know that this rotation is a linear mapping intuitively, but we can also check mathematically that this t defined in this form will be always a linear mapping. No matter what you have for a uppercase A, B, C, and D, okay, t sub any mapping defined in this way will be always a linear mapping. Please check it. And another example is a reflection. So reflection maps, okay, reflection about the x-axis is a mapping which maps A1 and A2 pair to A1 and negative A2. So graphically, given A1, A2 pair, the image is on the opposite side of the x-axis. So that the on the x projection mapping of often that will be a linear transformation, and projection maps A1, A2 pair to A1 and 0. You just replace the y coordinate with 0. That's a projection, orthogonal projection mapping onto the x-axis. So that is another example of a linear transformation. So if you came from engineering, probably you know many linear transformation like this, rotation, reflection. They are key functions in robotics and so on. So they are some examples of linear transformations. Now, given some m by n matrix A, I can map A to its transpose, then it will be a linear transformation, right? Because when we consider the the transpose, we I summarize some properties, right? So please remember that given A and B with the same size, the same m by n matrix, the transpose of A plus B will be the sum of their transposes, and C times A transpose will be C times A transpose. And if, yeah, so we learned this property. Of course, we also consider some others as well, right? Like if you take the transpose the two times, you get the original matrix back and so on. But I don't need this third one in this example. Okay, so since transpose satisfies these two, those are the requirements A and B in the definition of the linear transformation. So the transpose will be a linear transformation. And suppose that we have real valued function defined on the real line that have derivatives of every order, meaning we can we have the set of very smooth functions so that we can differentiate those functions as many times as you want. And that collection, that set will be definitely a vector space. And we want to consider one transformation T such that f any function, any differentiable function is mapped to its derivative. Then this will be a linear function because we know that the f given f of x and gx, what is the derivative of this sum? How do we compute this? We compute f prime of x and g prime of x and then we add them. If I multiply any number to a function, when this multiple is differentiated, you can multiply this c once you get this derivative. So these properties are very common properties of differentiable functions, and those imply that this differentiation operator, differentiation mapping, will be a linear transformation. So that will be a linear transformation. Okay, the differentiation is a linear transformation, then probably you can think of the opposite operation. In other words, the integration operation. So suppose that we have this space. So here C of R represents the space of all the continuous real valued functions. Given any real continuous real valued function, I can define, I can compute this integration of f from a to b. And we know that f plus g, if f and g are both integrable, then the integration of this is the same as, and when c is multiplied to f of t, that is c times integration of this from a to b. So we know this. We use these properties all the time, right? So that means the integration will be another linear transformation. And if if I consider a mapping from v to v, v to v, which maps x to itself, that will be a definitely a linear transformation, and that mapping will be called the identity mapping. Sometimes we want to consider a linear transformation from v to w, which maps every vector in the domain to 0. Okay, so in case of the identity mapping, I'm considering a mapping from v to v which maps x to x. Then that is called the identity mapping. But sometimes I can consider a mapping which is a mapping from v to w, which maps every vector in v to the 0 vector in w. Okay, such a mapping will be called zero transformation, and that is denoted by t naught. So these are some special transformation which are also linear. Now, given linear transformation, so T is a linear transformation from one vector space, say V, to another vector space W. Given this linear transformation, I want to define two spaces, two sets. One is the null space. Null space is the set of all the vectors in the domain, X in the domain, which are mapped to the 0 in W. So that is called the null space. And symbolically, we will use n of t to denote this null space. Sometimes this null space is called the kernel of the mapping. Okay. Kernel is used in several places in mathematics and in our class, in our linear algebra class. When I say the kernel of a linear mapping, then that is the set of the vectors in the domain which are mapped to 0. And in case of the, and then we define the range of the mapping, that is the collection of all the images. Okay, so the range is a subset of the codomain W, and this range may be called the image sometimes, and symbolically we use R of t to denote this image. So suppose that T is a mapping from V to W. Then the null space N of T is the set of all the elements which are mapped to the zero vector. So that is your N of T, the null space. And all the vectors in V will be mapped to some vectors, right? All the vectors in V will be mapped to some vectors in W. So the collection of those vectors in W will be called the image or the range of the mapping. So R of T is a subset of, so R of T is a subset of W, the codomain, and the null space is the subset of V space. Okay, so please remember. So the null space is a subset of V, and the range is a subset of codomain W. Please remember that. Okay. So here is an example. Suppose that V and W are vector spaces, and if I denotes the identity mapping and T null is the zero transformation which maps everything to zero, then in case of the identity mapping, the only zero vector will be mapped to zero. So the null space of the identity mapping will be just the zero vector only. The range will be the same as the domain, right? And in case of the T naught, all the vectors in the domain will be mapped to zero by definition. So the null space of T naught will be the whole space, and the range will be just the zero vector because every vector in the domain will be mapped to zero. One more example. Suppose that T is a mapping from R3 to R2, which maps this triple to this pair. Then the null space consists of the vectors such that this A1 minus A2 equals 0 and 2A3 is 0. So A1 minus A2 is 0. So A1 and A2 are the same, and the third entry will be 0. So that's why it consists of a vector of this form. And you can check that the range is the whole space. Please check this. Okay. So let's call it a day here, and let's call it a day here and see you next time. Okay. And if you have any questions, please let me know by email. Okay. Thank you for listening. See you next time.